In a process costing system, a factory produces identical, indistinguishable units on a continuous loop. Because the output is entirely uniform, the identical nature of each unit enables assigning the same average cost per item. But when a company produces many different products, each with individual and unique features, this math collapses. If products are manufactured to order, you cannot simply divide total costs by total units. A custom manufacturing environment requires a completely different accounting architecture to isolate the economic consumption of specific individual production runs. This document is the primary ledger for that environment, the PARCO job cost sheet. It serves as an uncompromising ledger designed to capture every resource consumed by a specific custom job, categorized across 3 cost pillars: direct materials, direct labor, and manufacturing overhead. Job order costing is a mathematical mandate. Without it, a factory lacks the capacity to track expenses and accurately price distinct goods. Building this ledger starts with tracking the first 2 pillars, which consist of verifiable direct costs. Direct materials are the physical resources that can be explicitly and economically traced to the creation of a specific job. This is the PARCO Materials Requisition Form. It acts as the physical evidence to authorize and track those specific materials. Looking closely at the data, this form quantifies the exact dollar amount of wood consumed specifically by job A143, which totals $116. This verified data is injected directly into the primary ledger. Under the direct materials column, requisition X76890 is linked exactly to that $116 amount. We then shift focus to the human element required to assemble these materials, direct labor. This is the PARCO employee time ticket, the tracking evidence required for human capital. This ticket mathematically locks a worker's time and hourly rate to a specific job number. For job A143, 8 completed hours at an $11 hourly rate verifies an $88 labor cost. Direct materials and direct labor represent exact, indisputable economic reality. They are directly observable on the factory floor. If all manufacturing costs were direct, the accounting system would be perfectly empirical. However, the factory floor hides a massive, untraceable blind spot. That blind spot is the 3rd pillar of costs: manufacturing overhead. Manufacturing overhead consists of indirect factory costs, including everything from machine grease used on the production floor to factory rent and the manager's salary. The core problem is tracing. It is physically impossible to determine exactly how much machine grease or factory rent was consumed to build one specific custom wooden crate. Furthermore, overhead is a volatile mix. It contains both variable costs, which fluctuate with production volume, and static, fixed costs, which remain constant. The final complication is timing. The actual total overhead expenses for a company are not known until the accounting period is completely finished. This creates a timing paradox. Management cannot wait until the end of the year to calculate the cost of a job they need to ship and build to a customer today. Returning to the job cost sheet, the process halts here. The manufacturing overhead column is entirely empty. Because manufacturing overhead is untraceable, mixed, and delayed, empirical tracking must be abandoned. The system must pivot to a mathematical allocation model to survive. The engineering solution to bypass the overhead timing and tracing paradox is the predetermined overhead rate, commonly referred to as the POHR. The POHR must be calculated before the financial period even begins, relying entirely on forward-looking estimates. The architecture of the formula is a ratio between 2 massive estimates. The numerator is the estimated total manufacturing overhead cost for the entire coming period. The denominator is the estimated total units of an allocation base for the coming period. The allocation base must be a rational cost driver, like direct labor hours. Let's test this formula using data from NWFab Inc. They estimate a total overhead of $760,000 for the year and expect to run 20,000 total direct labor hours. Dividing these estimates yields a predetermined overhead rate of $38 per direct labor hour. This provides the precise conversion rate required to charge invisible overhead to jobs in real time. The strict operational rule for applying overhead is to multiply the predetermined rate by the actual activity incurred by the specific job. Let's execute the final audit of NWFab's job WR53, starting by locking in its known empirical costs. Job WR53's trace direct materials cost is $200. Direct labor is 10 hours at a $15 rate, totaling $150. For overhead, we multiply those 10 labor hours by the $38 predetermined rate, applying $380. Summing materials, labor, and overhead yields a final cost of $730. This total cost is a hybrid artifact. It blends hard empirical facts with estimated allocations, masking underlying complexity beneath a single dollar amount. Zooming out, a completed job cost sheet is a triumph of operational system design, synthesizing highly disparate data streams. But direct your attention to the critical bottom section of the document, the cost summary, and its ultimate output. Interpreting this final average unit cost requires extreme caution. The manufacturing overhead applied to this job includes fixed costs, like factory rent, which are now permanently baked into this average unit price. The underlying economic reality is that if the factory decides to produce just one additional unit, the total fixed overhead of the facility does not increase. Therefore, the true incremental, out-of-pocket cost of manufacturing one more unit will actually be less than the stated average unit cost on the ledger. This average unit cost is strictly an accounting mechanism required for inventory valuation. It is not an exact predictor of future marginal behavior. Job order costing provides the logical framework to track custom manufacturing. True financial literacy requires understanding where empirical data ends and mathematical estimates begin.